Hello and welcome back. The purpose of this video is to continue our discussion on fluid statics and to derive an equation that describes what's called the buoyant force. So just to remind ourselves where we're at from the last video, we began to talk about fluid statics. We introduced pressure. Pressure gets the symbol capital P, and it's force divided by area. And so the units are going to be newtons per meter squared or a Pascal. We also define density. Density gets the symbol rho, and it's mass per unit volume. There are three different types of pressure. Gauge pressure gets the symbol P sub G, and gauge pressure is the density of whatever fluid an object is further submerged in. So this is not the density of the atmosphere on planet Earth. This is the density of a fluid that an object is additionally submerged to, as well as the atmosphere. So this is the density of the fluid times the acceleration due to Earth's gravity times how deeply the object is submerged. Atmospheric pressure gets the symbol PATM, and we will use the atmospheric pressure, sea level dry air. So that's 1.03 times 10 to the 5th pascals. And then the other type of pressure is absolute pressure, and absolute pressure is just the total pressure an object experiences. So if the object is on planet Earth and it's further submerged in some other fluid, then we have the gauge pressure, that's the pressure due to the further submersion, plus the atmospheric pressure, that's the pressure due to the column of air molecules that lie above the object as well. So it's just the sum of those two pressures, and of course they have to be in the same units to be able to add them together. So now let's consider an object that is got two dimensions as far as depth goes. So let's say we have an object in a fluid. So this is the density of the fluid. And notice that the object is further submerged, so it's going to feel a pressure. However, the pressure that it feels is going to be increasing as depth increases. So the pressure down at the bottom of the object is larger than the pressure at the top of the object. Let's take our equation for pressure. Pressure is equal to force divided by area. Notice that if I multiply both sides by area, I see that force is equal to pressure times area. So there's going to be a force felt on this object that is the product of the pressure at that point times the area. So if you look at the object on the top, we're going to have a force, which we'll call F1. And that force F1 is going to be equal to the pressure at height 1 times the area of the surface. So this will be our height 1, H1, right there. In addition, there's a force on the bottom of the object, and that force on the bottom of the object we'll call F2, and it's going to be at a depth H2 from the surface. So you can see that the pressure on the top is going to be smaller than the pressure on the bottom. Remember, this is gauge pressure, and actually before we re-express those pressures, let's make an argument for the sides of the object as well. We're going to have forces being exerted on the sides of the object which are going to increase with depth. But for every force that's pushing to the left on the right side of the object, we're going to have a force pushing to the right on the left side of the object. So these forces right here are going to all add up to 0. These forces will all cancel on the sides of the object, but notice that the forces top and bottom will not be canceling. So pressure P1 is a gauge pressure, so I can write the gauge pressure as the density of the fluid times the acceleration due to Earth's gravity times how deeply the point is submerged. The top of the surface is H1 below the surface times the area. And F2, the force felt on the bottom of the object, is P2. That's a gauge pressure as well. P2 is the density of the fluid, acceleration due to Earth's gravity, times H2, times the area. So there is atmospheric pressure above these. Those atmospheric pressures are the same. So these are the forces being felt on top and on bottom of the object. And notice that there is going to be a force upward that is larger than the force downward, because again, all of these terms are the same in F1 and F2 except for H1 and H2. H2 is larger than H1, therefore F2 is larger than F1. The difference in these two forces, the unbalancing of the force upward and the force downward, creates what we call a buoyant force. And this is the reason why it is easier to move an object when it is submerged in a fluid, in an additional fluid, than it is when it's not submerged. So I don't know if you've ever had this experience where you're playing in the water and you want to move something that's fairly heavy, like let's say a boulder in a river, and it's movable, where if that same boulder was outside of the river, you would not be able to move it. And it's because you're getting a help from the buoyant force. So you're getting some assistance there. The buoyant force gets the symbol F sub B, and the buoyant force then is just the difference on the force upward, which is F2, the force pointing upward, minus the force downward, F1. And so plugging in these terms then, the buoyant force is going to be equal to F2 is the density of the fluid, acceleration due to Earth's gravity, times H2 times the area, minus F1. F1 is the density of the fluid, acceleration due to Earth's gravity, H1 times the area. And I'm going to go ahead and factor these common terms out so that the buoyant force is equal to the density of the fluid times the acceleration due to Earth's gravity times the area. And what do we have left when we factor out these common terms? Well, we have H2 from the first term minus, and when I factor out the same common terms, H1 is left over from the second term. Notice that this product right here, the area, and again, this is the area of the object, so that's the area A, times the difference in height is the height of the object. So if I take H2 and I subtract H1, I have the height of the object. So this product or this subtraction right here, this is the height of object. And if I multiply the height of the object by its area, I have the volume of the object. So the buoyant force then can be written as the density of the fluid times the acceleration due to Earth's gravity times the volume of the object. Now, if only part of the object is submerged, then we would just use that part of the volume of the object that actually lies beneath the surface. In other words, if I have a vat of fluid and I have an object that is only partially submerged, then this part of the volume right here is the part that I would use in the buoyant force equation. So use only volume of object that is submerged. So sometimes you'll actually see V submerged substituted in for V object. That just means that not the entire object is submerged, but only part of the object is submerged. And so that's what the little SUB is standing for underneath that volume. And let me just move it up a little bit because I know it's cutting off from the video a little bit. So let's write it up here. So that's the subscript submerged. Okay, so we'll pick up here next time and we'll talk about the relationship between the object's density, the density of the fluid, and how much of the object is submerged versus the entire volume of the object in the next video. So we'll see you next time. Thank you.